The next question is, what was the difference between skew and frame and its purpose? So, understandable confusion. I had it myself as well for quite some time. And eventually, I came to one conclusion that they literally represent the same thing, but within radius, their usage is very peculiar. If you are looking at frame, you use the frame only for the imposed velocity. So the imposed velocity is the only place where you'll try to use the frame, whereas all other boundary conditions you'll try to use a skew. They literally have the same type. I mean same inputs, same outputs, but yeah, skews are the ones which are more commonly used when you're trying to define the solution or trying to set up your model. Now, frame keyword, you'll use it more often when you're trying to look at the results. So for example, if you load your animation in your Hyperview and you want to now, because you had forgotten to probably create some system in your simulation, now you want to still measure your deformations or intrusions with respect to some local system. That's when you'll define a frame, but this frame it doesn't represent any card, that radius card that we always talked about. This frame is very much particular to Hyperview. That's where you'll define a system or a frame, and you will try to use this frame to measure the results. So measuring the results is one application of frame, or imposing a velocity is an application for frame, but from radius standpoint. The measurement of results using a frame is an application from Hyperview standpoint. Not very, what I can say, not very standard about a software. You don't have to remember this, to be honest. You can easily forget this, and you'll still find, going to any software, you'll find some way to create the system and using it nicely. I also have an explanation of this skew and frame. What I'll do is I will try to copy the link to that particular PDF in the chat window. Actually, I'm not sure if we can attach the files in this chat window. That would be even easier. How to decide between master and slave? Very good question. So master is the one where, or slave is the one where your analysis is. If you're trying to analyze your table, when you're hitting it with a hammer, your table is the slave. Well, if you're looking at a car in a crash, your car is the slave entirely, whereas your barrier is a master. If you're looking at an occupant and an airbag, your occupant is the slave, your airbag is the master. So that way, by this logic, wherever you're trying to run your analysis, your object of analysis is slave. Then there are more criteria being used now. Now, whenever you're trying to see that both the components in your system are actually the ones you want to analyze, in case of table and hammer, both my hammer is important for me and also table is important for me. Now, in that case, it's self-contact is the only way to do that? No. Self-contact is one of the ways, of course, but it's very costly. So in other ways, what people also try to do is the one that is stiffer among the two will become a master. The one with less stiffness, that means lower Young's modulus, will become a slave. There is also some table I have shared during the lectures, but let me see if I still have it. Yeah, and these are 3 or 4 points I had mentioned in that table anyway. That the one with more stiffness, or the one where you are not so much interested in your analysis, those are the ones which usually become master. In case of weightage being same, you are interested in both, and your stiffnesses are same. Then in that case, the one with the coarser mesh, if your mesh size is higher, make it a master. If your mesh size is smaller, make it a slave. Because again, the same thing. Smaller the mesh, smaller the time step, better the results. Time step comes at a cost, but you want accurate results or more accurate results compared to less accurate results. So slave becomes the one with the smaller mesh size. Inversely, you can also say that if you already know which is supposed to be master and which is supposed to be slave, you can go with a coarser mesh on master, whereas you have to be very careful on slave about your meshing. So go well on the meshing when you're trying to mesh the slave. That means cover the geometry properly. When do we use type 7 and type 11 contact? Type 7 is node to surface to node contact. So your master is supposed to be a surface, your slave is supposed to be a node. Very impractical, right? Because nodes, how do you even imagine that? But what that means is it's not a sufficient contact in many cases. So your master surface is going to go after individual nodes. And there will be cases around the edges of the master where your slave nodes have simply gone past that, but none of those slave nodes have really violated any condition for being in contact. And that's when you need the edge to edge contact as well. So edge to edge contact is when even the element edges will be taken into consideration, or the lines joining those nodes, which are basically the elements, these will be taken into consideration, and the edges will use the same kind of intelligence to detect another edge. So when you combine your surface to node with edge to edge contact for the same surfaces with same master and slave, that's when you make a proper surface to surface contact. So to be honest, surface to surface contact is the best contact you would want, or the most complete contact you would want. Now, type 24 in radius is already a surface to surface contact, but there is clearly a difference there. Type 7 is a nonlinear contact where in physical world, if you try to push against a surface, more you push, more the resistance you feel. That's the nonlinearity you need. Whereas in type 24, your resistance or your stiffness of the contact stays consistent throughout, which is not very realistic. But then type 24 has been called more stable for solid elements. So only for solid elements we use type 24. Whereas type 7 and 11, you will try to use everywhere for shell elements. Now, surface to surface contact has also been defined in type 19, which is one of the recent developments. Now, by recent, I'm still calling it, let's say 10 years ago, it was developed or released. Now, type 19 is basically combining your logic from type 7 and type 11. It's basically the difference between surface to node, edge to edge, and surface to surface. Whereas type 19 is your surface to surface, which is all equipped with nonlinearity and everything else. How to decide the time step and runtime. Time step, we already said how to decide that. Smallest element, do the calculation with the smallest element and calculate your critical time step. Your time step of the simulation needs to be anything more than the critical time step. Simply put, runtime of the simulation. It's hard to say, but depending on your simulation and the amount of deformations you are expecting, or the type of analysis again, if I'm doing a sled test where only the occupant and the airbag is involved, 150 milliseconds is fine. If I'm looking at a full crash analysis, I would need somewhere around 200 to 250 milliseconds minimum. For a simulation that I need to submit to the government agencies, I have to run the simulation for 300 milliseconds. So that's a typical runtime. Now, in the projects that you will do in this course, the runtime has been set up for 80 milliseconds, if I remember it correctly, because the amount of deformations we are looking for are pretty minimal, because we are doing a subsystem analysis there. We are first testing all the frontal structures, then we are doing all the side structures. So 80 milliseconds are sufficient there for us. If we use rigids for connecting subcomponents of a car, then we are facing the energy error of 99%. Why has it occurred? I think this problem needs to be looked at in more depth. That means you will have to share your screen sometime soon and we can look at it together. Using rigids to connect the subcomponents of a car. So what we can do is probably make some meaning out of positive energy error. That's the only way to go here with these many details. The positive energy error usually comes when your kinematic conditions are not defined correctly. Energy has been created in your system, but why will it be created? If you are using QEPH shell formulation, of course, the energy error can be positive. This is textbook, but yeah, it might be worthwhile to look at the model more in depth because incompatible kinematic conditions can be the only reason. Incompatible kinematic condition, by that I mean the rigid bodies or welds again, which are kinematic conditions, and those are the ones which can lead to large positive energy. There is no clear textbook method of saying, okay, you see 99%, so do this definitely. We have to look at the simulation and go case by case. Okay, going to the next question. How far we are? Okay, we still have little time, not much. So I'm going to skim through questions now. Recommended mass and energy error value for explicit and quasi-static. So for explicit, it depends on the company to company. In an ideal world, you should keep your mass error below 2%, energy errors between +5 to -15. But closer you are to zero, because these are all errors, closer you are to zero, better you are. But like I said, whenever you use QEPH elements, like the type 24 elements that we usually use, they naturally add some energy in your simulation. So positive energy is going to be there. That's why +5 is allowed. But yeah, don't go below or don't go beyond +5. So of course, 99% is a clear violation. For quasi-static analysis, mass error is not much of a problem. Energy error can be a problem. Why mass error is not a problem? Because quasi-static analysis is a different analysis from explicit. Here, your deformations are not happening because of acceleration or velocity. So when your mass or change of mass gets involved with your velocity or acceleration, you're changing your momentum. And if you remember the Newton's laws, it's all about the momentum when you're talking about such crash problems. Rate of change of momentum is basically the force. Now, the momentum has mass as one of the important factors, but if the mass is consistent, which is the case with quasi-static analysis most of the times, you're not really worried about the mass error anymore. Also, the velocities in quasi-static analysis are pretty minimal. So even if you keep changing your mass in some way, you manage to change your mass, let's assume, your velocities are almost close to zero. You are just implying some displacement at a very slow rate, which says that your velocity is nothing or nowhere. So it doesn't represent anything there. So because momentum is not getting involved in quasi-static, you're not so much worried about mass errors. Energy errors, you'll still have to keep in check because energy errors can be coming from, again, incompatible kinematic conditions, which can diverge your solution or run your solution into unanticipated errors. For crash simulations, do we give gravity loading or not? Yes, we do, but you have to have tires and you have to have a floor for that. In our case, because we are doing subsystem analysis, we did not use the gravity in our projects, but when you are running the full crash simulation, I have also given the full car model there in one of the assignments, just for fun. So if you try to decide, or if you decide to run that entire car model, you can run that when you don't have a student edition, but you have a full scale edition of HyperWorks. So you can run the full car model, and that's when you will need the gravity loading, because you need the components to fall down when they get disconnected or get broken away. What is meant by contact energy? I think we already discussed.
I want to ask one question. For quasi-static, what the energy error you said? What the percentage of energy error you said?
Let me tell you if I have it handy. So energy error for quasi-static has to be below 1%, up to 1%. So I think for quasi-static, the condition you should check is your kinetic energy, which is again represented by the velocities and masses. It has to be less than 1% of your total energy. That's a high level check. If you are within that check, then probably your quasi-static simulation will not cause any errors or any issues. Of course, there are chances that you will also run with 99% positive energy. That means, again, your welds are wrong or your rigid bodies are creating some problem. But a better check after energy error for 99% is kinetic energy to be less than 1%. If the kinetic energy is more than 1% of your total energy, then you need to reconsider your simulation, or you need to consider whether it needs to be quasi-static anymore. The cards that you'll use for solving such problems is completely different set of cards than your usual explicit analysis. I wish I had a better, more clear answer, but yeah, that's all I can find on that particular topic. Okay, coming back to the list of questions. Importance of EPS max value in Cook's law. EPS max means your element plastic strain maximum. Now, the plastic strain maximum can be decided only by the laboratory tests. You'll do a tensile test. You'll see eventually when the component is breaking, what was the strain by using the strain gauge, and that you will use in your Cook's law, Johnson-Cook's law. So these values that we use are decided in the laboratories or in the labs, and then we use them in simulation. That just defines, or basically when you try to test such material models with EPS max value, you set up a tensile test itself and you try to see how it compares with what you saw in the lab. If it compares very well, or if it matches very well, that's when you get the confidence of using it in the crash analysis or other applications as well. D1, D2, D3, how to decide the value for it. There is a formula. If you go to the Radius help manual, just search D1, D2, D3 and you'll find some formulae. If you don't remind me about this, I think I had searched that page somewhere. Let me also try that. We are running out of time, but right. So there is indeed Johnson-Cook. So there is a card called /fail/Johnson. That's where you will see in the bottom a formula for how to calculate the D1, D2, D3. It's like a equation with three unknowns. So you have to have three equations to solve those three unknowns, of course, in an ideal world. But many times you can go with assumptions there that to calculate strain at a particular time, what can be your stress and what can be your residual strain at that particular moment. So maybe I can share the link quickly in the chat window if it allows me to do that. Right. Okay. Moving on to the next question. Energy balance in crash simulation. Very clear answer provided in the course lectures. I think you can refer to that. Energy balance means that your total energy being created in the system, not created in the system, it's the law of conservation of energy, to be honest. The energy at which you start your simulation has to be consistent throughout the simulation. So when you see your energy errors are negative in the simulation, that means you have lost some energy. That comes from energy lost in hourglass, contacts, and things like those, which are not a part of your system anymore because they have been lost, maybe due to friction, due to heat, due to hourglass again. Whereas there are cases where energy could be added in the system as well. For example, in case of airbags, it's very typical that energy gets added in the system. That's when you'll see the external work is also being accounted there. So lot of things to be considered, but energy balance has a clear formula. Just follow the lectures. Also, you can search this easily on the Radius help manual. Just type energy balance and you'll see that formula, which I have discussed in our lectures. What was the purpose of failure card? We discussed element deletion and elements being cracked. That's exactly the purpose of failure card. Basically, failure card is giving you a way to detach an element from your simulation when it becomes non-realistic. Because your material curves are not perfect. Even though they are being prepared in the lab, your stress strain curve for a material is not perfect. So what you do is you set a failure point. In the lab, if you see that after 25% of strain, if the material is going to fail, that's what you say here. In the lab, what will happen is reaching this 25%, that path is different. So either you can use a stress strain curve, like literally by giving point by point, or you can decide Johnson-Cook card where you have given only the main parameters, like what should be the elasticity, then what should be how the curve should look like. So all the Johnson Cook curves have been generalized using 3 parameters. And those 3 parameters usually give you a nice correlation between all these curves. And add a failure card to that, it makes it almost perfect. So that's the purpose of failure card. When you have a Johnson Cook material, your simulation runs faster. And if you're not worried about that error in the end, you're set to go. Importance of D-search and how to decide the value. D-search, I think you're meaning, what's the meaning of D-search in rigid wall? Well, you're just setting your search distance for rigid wall to find its slave nodes. So the usual value can be 200 or 300 mm. If your simulation happens to be so fast during the impact, you can set a higher value, let's say 500 mm at the most, but don't go ever beyond that because it increases the simulation time, because then your rigid wall has much more work to do while trying to find the elements. Career aspects for BE graduate in analysis domain as fresher. So if you are lucky to be placed in a company through your campus placements, of course, you'll get opportunities to do the analysis right away. If you're not so fortunate with your college or with your university, then there are chances that you're trying to search for your job on your own. So in such cases, making connections in the industry is useful. If you can ask for referral, that is also useful. That's one way to get into this domain, first of all. If that doesn't happen, you still have your ways. You can still look for supplier companies, which are easier to get in. Once you gain some experience from supplier companies where you have more exposure, they may not only expect you to do one of the beginner tasks, but they will also give you exposure to do more analysis or spend more time on solving a problem from A to Z. You want to be in such environments where you can get that exposure. So that's one way to get started. And after that, you can see whether you're liking the type of product you're designing or you want to switch. That's how you can grow in this career or in this stream. The odds for getting jobs abroad as fresher, not really a question that I can answer as a generic number. Again, the hard work and having the right skills acquired at the right time really helps. The knowledge you acquire right now, whatever you mention on your resume, you have to be very thorough with that. Not on your resume, you have to, of course, summarize it on your resume, but whenever someone asks you a question during an interview, you have to be ready with a proper answer. There is a lot that goes behind getting a job abroad. So yeah, hard work is one essential factor. How to upskill in this domain when we get only basic knowledge over internet or from Skilling. Upskilling comes from experience eventually. So when you're learning this course, you have 3 projects, but of course you can also work with the teams of TAs that we have in this course who are also trying to develop some more projects. So you can try to solve more projects in general, and you can work with some companies to, of course, do more projects. Project experience is the only way of upskilling. I can learn Radius today, I can learn LS-DYNA tomorrow, and then I can learn some other software another day. But you'll realize eventually that software is only a tool. You need to have the physical understanding or meaning of it. When I'm using a time step, why am I using the time step this way? So yeah, you're going to learn it in Radius course. If you do, or if you try to learn LS-DYNA, you'll understand that, so you'll understand that you are applying literally the same technique, even in the other solvers. So just listing the number of softwares is not going to help us. To upskill really, we have to have that experience of projects. So you have to apply your knowledge in various problems before you can say that, okay, now I'm ready for an even bigger challenge. So upskilling means that grabbing that confidence from somewhere to go for even bigger problem. Okay, then coming to the chat, now that we have finished all these questions, what's the reason for that type of deformation? I think this question was in connection with hourglass. Because that was the only place where we discussed the deformations, right? Yeah, so the hourglass deformations, what happens is you have a concentrated force happening at a very rapid rate. When that happens, it's like your deformation of the element is skipping it's happening so fast that it is even skipping your time step. So your time step one and your time step two, your time step one says that, hey, deformation of this element is at 5%. And your next time step says, hey, but you know what? I didn't see at 5%. I saw it directly at 15%. So this 10% in between has been lost. That's only the beginning. When hourglass deformations happen, you'll see that elements are getting deformed. Like your element of 5 size can grow as big as your laptop size. That's a funny part of hourglass deformations. Now, what is the difference between dynamic and transient dynamic? Well, so dynamic typically means the ones that is coming from vibrations. Now, transient dynamic, well, I have never come across a category like that, to be honest. But let's try to make us meaning out of it. So the word transient means something that changes over time. Dynamic, it's something that is constantly changing, more like a vibration. So with dynamic, you can think about vibration. With transient, you can think about something where for every second or every millisecond, something is changing there. It's things are moving from one end to another end. It's transient. Things are vibrating at a constant rate. It's dynamic. We can think about some examples on that lines. I don't really have, or I can't think about example right now with us running out of time.
Sir, so we can say that the crash simulation is a transient dynamic, not a dynamic one.
Correct. It's a transient analysis.
So, but up until now in that coursework, we are saying like crash analysis is a dynamic analysis. But you are saying
Yes.
right now that it's related to the vibration.
Yes. So dynamic, the word dynamic comes from the vibrations. So if we go deeper, why transient dynamic, or why do we call the crash analysis as dynamic? It really comes to the shock wave. What is the shock wave? It is creating a sense of, or it's creating those vibrations in your structure when it's getting hit from one end and you're experiencing the shock on the other side. If you being the occupant, if you're experiencing the jerk inside your car when the bumper, which is let's say 3 or 4 feet away from your legs, is hitting some barrier, you're still feeling that jerk, right? So that is because of all the vibrations that have transferred. It's really the shock wave that is doing all this trick. So in a way, it is dynamic and it is transient because every frame is different. So that way, yes, crash analysis you could call transient dynamic. How to call out and position the dummy model for the crash analysis. If you have the model, please share with us so we can try on our own. Well, the dummy model. So for the student edition, I could not get the entire dummy model. But if you want to try the dummy positioning, so when you download the HyperWorks, you also download some of the help files. So there is a tutorial on Radius HyperCrash where they have used a dummy positioning method. So if you follow that tutorial, that's pretty much what we do in dummy positioning. Unfortunately, I did not have a realistic model because if you follow the course, later on I have described why getting a dummy is a challenge, because dummies are owned by very few companies, let's say a couple of companies across the world, and they don't share dummies for students. They share dummies only for the companies who pay for those licenses. Unfortunately, that's not the case. And those dummies usually cost millions of dollars. So it may not even be economical to get those dummy models for everyone.
Suppose we have to do a dummy analysis, okay? So after calling out main vehicle model, complete vehicle model, okay? Uh, how can I import that dummy model? Is that any special option available for dummy model to call out and positioning, or we have to make a complete
Yes,
pack? Okay.
exactly. So if you follow the tutorial, they have exactly explained all these steps, how to import a dummy and how to position it properly. So these preprocessors like HyperCrash, HyperMesh, they have a special dummy positioning tool that helps you do all this job. So it will, if you select the proper dummy, then it already knows where is dummy's hand and where is dummy's head, and it will provide you easy ways to rotate the dummy hand to a particular angle, rotate the dummy legs to a particular angle, and then you will say how to place it or how do you want to place it on the seats. So all those things will come into pictures if you follow the tutorial. But that's a good tutorial to get started. In reality, there are more challenges like seat deformation. When you're sitting on a seat, of course, the seat gets deformed under you. That also needs to be calculated somewhere. You cannot imagine that the seat is undeformed while you're sitting on the seat. So that's one small simulation that you have to run, or pre-simulation they call it. The tutorial may not have that pre-simulation. I think it might be available only when you actually get into a seating supplier or an OEM. Again, it's a thing that is hidden behind all those licensing doors. Can we consider an example of testing the vehicle on a continuous 5 to 6 speed breakers? You can try that. I think in that case, your objective of the analysis is no more regarding the frontal structures. You will be more associated or more worried about your underbody structures, and you'll be more worried about defining your suspensions properly. So in some companies like Tesla or Jaguar and Land Rover, so when I was working in Jaguar and Land Rover in my initial stages of the career, we have done some analysis like that. What we used to do is you take a car, it can be an SUV or of course, sedan, and you try to run it over a block of stone. Now, how high that block of stone needs to be, that is up to the company, and that's the name of the game there. I mean, they won't share that information to everyone, but this is the overall concept, that you try to set a block in front of your car and you try to run your car over that block. When that happens, if your suspensions are correctly modeled for your simulation, your bumper will scratch over that block, and when that scratching is happening, your car might feel that bump under that. So your car will jump a bit. If it doesn't jump, probably it will scratch against your underbody, and you have to now analyze whether it is damaging your engine mounts or your battery or your fuel tank or anything like that, or even your suspension arms, lower suspension arm, or your joints. So all those things will get under scrutiny. So typically, even on the roads, if you look at the way we have designed speed breakers in India, where every village decides their own design of speed breakers, if you run your car at a high speed over those speed breakers, you must have experienced that sometimes it scratches your underbody. Whereas if you go slow over it, it may not do that. This is exactly the analysis that we tried to do when we were doing that. And we wanted to make sure that the ground clearance is good and the underbody components are very well designed, that they can cushion when such things happen. So they can cushion against such deformations, so that the engine mounts and the fuel tank can be saved from such issues where it suddenly gets hit with speed breaker or blocks on the road. Can you explain the nodal time step and element time steps in Celestina we are using and speaking everything with element time step? One thing I couldn't understand, how node can have stiffness, but in terms for the element, it can have stiffness. So yeah, basically element is the one which represents your material. So it is the one which will have stiffness. The nodal stiffness comes into picture when you are trying to talk about nodal time step. And the nodal time step, you're trying to talk about the mass additions. These are all interconnected or intertwined problems, concepts. In layman's language, what you would do is, if you have a shell element with 4 nodes, you'll simply split it into 4 different parts, and you will consider those 4 parts to be concentrated on those particular nodes. Now the stiffness that you had, the average stiffness you had on the overall element, will be the stiffness you had on every node as well. But now if your 2 elements have 2 different stiffnesses, let's say element 1 has 1 stiffness, it shares 2 nodes with another element, it has different set of stiffness. Now that's a place where your nodal stiffness will be little challenging to calculate. That's when you'll either average it, or so averaging is mainly the way to go after it, or you'll try to see whether your node is closer to one element centroid against the other element centroid. So you'll say, or you'll try to use a weighting technique. Those are I mean, there are many ways of calculating nodal time step. I think we need to decide, or we need to discuss that topic in more details next time, because yeah, I do see nodal time step question being asked quite a few times. So it might be worthwhile to discuss that in more details in one of these lectures. So let's do that when we meet again. I have to run now. I have run 20 minutes more, so let's close this session. For symmetry contact, there is an easy method in Hypercrash where you simply check that card, and once you add that contact, it will create a contact for you automatically. There is no symmetry contact, but it will create a mirror contact for you. Okay, that's all about it. Let's conclude this session right here. Thanks a lot, everyone, and have a great rest of the evening. We'll meet again.